Welcome, everyone. Thank you for taking the time to join us in our discussion today. I am your host, Hunter Wiley, and today we will be discussing some of the fundamental terms and definitions of ultrasonic flow measurement. In addition, we will look at how this ultrasonic theory is applied in our Panametrics flare gas flow equipment. A little about myself. My name is Hunter Wiley, and I am the Panametrics Global Services Training Leader. Prior to this role, I served as a field service engineer across North America for 4 years, servicing products across the Panametrics portfolio. Before that, I received my Bachelor's of Science in Petroleum Engineering from the University of Houston. I'm extremely honored to be speaking with you today. As the Global Services Training Leader, I have modified the content we will be discussing from our instructor-led training courses. These courses allow for a strong understanding of our equipment for technicians, engineers, and supervisors, and are customized based on the relevant field equipment in use at your specific facility. Our experienced trainers combine proven teaching skills with hands-on application for a highly acclaimed learning experience. For more information, you can visit panametrics.com/training. Before we go any further, I would like to take just a minute to offer a brief safety moment. During these ever-changing times, it's important to focus on your physical and your mental health. Like many of us, you may be stuck behind a computer screen at your home, while others may be continuing to operate at facilities. Wherever you may be, please be sure to stay active. Take breaks to move around, perform stretches at your desk, and even take a walk if you're able. Find a way to connect with others. That may be through telephone or video calls to your family, friends, and even coworkers. Be sure to eat well. This is one that I'm personally working on. Meal prep may be a hassle at first, but it will pay dividends throughout the week. And finally, get some sleep. Find a way to limit your screen time, and especially for those of us working from home, ensure you hold to a set time so you can leave work. A quick history of Panametrics before we get going. Founded in 1960, Panametrics started off as a moisture measurement company. Though ultrasonic transducers were developed in the late 60s for non-destructive testing, Panametrics repurposed the technology for transit time flow measurement in liquid applications. Since that first commercial flow meter in 1979, Panametrics has continued to revolutionize ultrasonic flow measurement in various process conditions, while simultaneously growing its initial aluminum oxide probe hygrometer into a full portfolio of gas and moisture analyzers. Many industries recognize our legacy of excellence and our ability to provide solutions to even the toughest applications. We are Panametrics, a Baker Hughes business. We will begin with some fundamental terms and definitions that are used in ultrasonic flow measurement. But before we get into that, what is ultrasonics? To get that answer, let's take a look at the different types of sounds. Sound waves are vibration energy that travel through gas, liquids, or solids. Sounds can be classified by the frequency ranges as shown on this page. The most common sound waves are those that we can hear. These sounds fall in the range of frequencies between 20 Hz and 20,000 Hz and are called acoustic or auditory sounds. Sounds with frequencies below the acoustic range are called infrasounds, while sounds above the acoustic range are called ultrasound. An example of infrasonic sound waves is the communication of whales. These animals send sound waves through the water across many kilometers using a very low frequency sound wave. Baleen whales in particular use a bristled plate to generate these deep sounds for tasks like location, migration, mating, claiming territory, and more. When it comes to auditory sounds, us humans are quite familiar with what these sounds are like. We use sound waves every day in this frequency for many uses, such as to detect things like a falling tree or an approaching car. Of course, another very common use of audio sound waves is in normal conversation where one person speaks and the other listens. Ultrasonic sound waves have a higher frequency than infrasonic and auditory sound waves. Dolphins use organs in their forehead to emit bursts of ultrasonic sounds and then listen to how the sound bounces back to them. The relatively higher frequency of ultrasonic sound provides an echo that has a higher resolution. This resolution enables the dolphin to distinguish between a fish, which could be its lunch, and another object like a floating piece of seaweed. From the title of this section, you likely know by now that Panametrics flow meters utilize sound waves in the ultrasonic frequency range for sounds. But how are these sound waves transmitted? Sound waves rely on a process or a medium to move from one point to another. The definition of this process depends on its state of matter. In each of these states, the sound wave has to jump from molecule to molecule. The closer together these molecules are, the quicker and the better the sound wave can be transmitted across that medium. For gas processes, these molecules are spread far apart. This is considered a relatively low density process. As we look at liquid, the molecules are closer together, allowing for more signal to easily traverse from one side to the other. Now on the right of this spectrum, we have the solid materials with their molecules packed tightly together. While this state of matter has the highest density, it can allow for the best transmission of sound waves. Now, I should mention that each of these states of matter fully depend on the specific molecular structures, temperatures, and pressures to define the density of a specific process. That is why a gas process with hydrogen does not typically allow as strong of a signal to be transmitted through when compared to a similar volume of natural gas. Similarly, the same can be said between a heavy liquid crude oil when compared to wastewater. Density also plays a role in the characteristic sound speed of a process. Sound speed, or how fast a sound wave travels through a material, depends on many factors, but tends to change with the state of matter and the process conditions. In general, for gas applications, sound speed will increase as temperature increases. Alternatively, many liquid sound speeds tend to decrease as temperature increases. Of course, there are always outliers, particularly in this case, water. Up until 74 degrees Celsius, or about 165 degrees Fahrenheit, the sound speed will increase in water. Above this temperature, however, the sound speed will begin to decrease until the water vaporizes. On the right of this screen, you can also see a list of some sound speeds for various processes. Note that the sound speed in liquid water is over 4 times that of the sound speed of air, and the sound speed of solid stainless steel is more than double even that. Just from seeing these different sound speeds, you can see how density of a process affects the transmission of an ultrasonic sound wave. But what else can affect a sound wave? Now that we know how sound travels through materials, it is important to know that there are 3 distinct ways we can lose this signal. In ultrasonics, these 3 methods are collectively referred to as attenuation. The first one, dissipation, occurs as the ultrasonic wave propagates through a medium. Take, for instance, the ripples that are generated when a pebble falls into a still pond. The farther the waves travel from the initial source, the weaker they become until they're not even distinguishable from the rest of the water. This method of attenuation is most common with hydrogen-rich processes. As the signal tries to jump from one molecule to the next, the overall strength of the signal decreases rapidly. Reflection occurs when a sound wave bounces off of an object. We can see this in action when we hear an echo as the sound wave bounces off of a wall and comes back to us. In ultrasonic flow measurement, we can actually bounce a signal off of the opposite side of a pipe to be able to get a flow measurement. However, reflection is not always our friend. Second phase materials, such as a solid catalyst in a flare line or gaseous bubbles in an oil pipeline, can cause the signal to bounce away in a different direction than what is expected. Absorption occurs when a sound wave is absorbed by a material until it is reduced or even lost. Some materials like this may have rough or even porous surfaces. A soundproof room is where there are many of these layers of materials that absorb the sound wave. In ultrasonic flow, this can be observed with process buildup, corrosion, or even some attenuative gases, such as carbon dioxide. Each ultrasonic flow meter by Panametrics has an automatic gain control, or AGC, which controls the amplitude of the transmitted signal to compensate for attenuation in varying flow conditions. However, there is always a point where too much attenuation is simply too much to overcome. With those fundamental terms and definitions aside, let us look at how a Panametrics ultrasonic flow meter operates using this transit time theory. Let's first look at how the signal is generated to start with. We utilize the piezoelectric effect, which is the ability of a certain material to generate an electric charge in response to an applied mechanical stress. In Panametrics ultrasonic transducers, we use this phenomena for signal generation and reception. Piezoelectric materials are characterized by a relationship between voltage and mechanical energy. An ultrasonic sensor uses this characteristic to both generate and detect sound waves, as illustrated on this page. When the transducer is transmitting, the circuit will close and be completed, causing current to go to the transducer crystal, exciting it, causing it to vibrate and generate these sound waves. On the receiving end, the receiving transducer is listening, so that circuit is closed and completely listening until that sound wave strikes the crystal, causing it to vibrate, and then that vibration is turned into electrical energy to be returned to the meter electronics. As you can see in this demonstration, the sound wave is generated by one transducer, travels across the process, and is received by the other transducer. That second transducer then transmits a separate signal going back across the process, where it's then received by the first transducer. You can also tell by this illustration that the velocity of the process flowing through the pipe will affect the total transit time in each direction. When the signal is going in the same direction as the flow of the process, the signal goes faster when compared to the signal going against the flow. These transit times in each direction are used to calculate velocity, which we will look at in just a few minutes. In addition, both transducers are required for flow measurement. Just like you need two people to have a conversation, we need two transducers to talk back and forth for flow measurement. All right, I know there's a lot going on in this image, so let's talk through it. This is a typical wetted gas installation. We call it wetted because the transducers are physically in contact with the process inside of the pipe. Let's start by naming these transducers. With the flow going from left to right, the first transducer the process touches, the one in the top left, is called the upstream transducer. The matched pair of that upstream transducer is called the downstream transducer. The time it takes for the signal going from the downstream transducer to reach the upstream transducer is known as the transit time upstream, or T-up. The time the signal takes to go in the downstream direction, or with the flow, is called the transit time downstream, or T-down. The flow meter will need to have the path length, P, entered as a known fixed parameter, so the proper sound speed and flow velocities can be calculated. In addition, the axial length, or L, is measured along the direction of flow in the pipe between the two transducers. These two dimensions, P and L, are used by the flow meter to calculate the angle of attack and determine the velocity of the process flowing through the pipe. Other parameters to note are the outer diameter, the OD, and the wall thickness. These two fixed values are entered into the flow meter to calculate the ID, or the inner diameter of the pipe. For a circular pipe, this ID lets us calculate the cross-sectional area, which allows us to find the total volume of gas flowing through the pipe. One important thing to note is that this is the actual volumetric flow rate. For many customers, regulations exist that require flow to be normalized or standardized to certain temperature and pressure conditions. For this, our flow meters can accept a live temperature as well as a live pressure input from field transmitters. You can see those in the top right of the pipe. This standard volumetric flow is often represented in terms of standard cubic feet per hour, SCFH, or standard cubic meters per hour, SM3/H. So how do our flow meters use transit time to calculate velocity? If you're like me and find enjoyment in a complete set of derivations that lead to a final formula, feel free to take a look to the right. But if you think I'm a little on the weird side for liking formulas the way I do, please just forgive me and remember I'm still an engineer. Ultimately, the entire basis of transit time theory depends on comparing the transit times in both directions. If both the upstream and the downstream transit times are equal, then there's no flow present. As flow begins to increase, the T down value will be smaller than T up, resulting in a positive velocity. Another calculation that is obtainable through transit time ultrasonic flow measurement is sound speed. As we mentioned before, sound speed is simply the velocity of a sound wave through a given medium. In this case, we can look at the sound speed as the distance the sound wave travels in a known time interval. Our distance is a fixed value, that's your path length or your P parameter that we discussed earlier. The time is simply the average of your two transit times. As a word of warning for those of you that want to check my work or do these calculations on your own, you need to ensure the units and scaling all match up. Units of velocity and sound speed are typically in feet per second or meters per second, while the units for the path length are inches or millimeters, and units for transit times are typically in microseconds. The next calculation that our flow meter will perform is the volumetric flow measurement. To get this, the meter simply takes the actual velocity that's flowing through the pipe and multiplies it by the internal cross-sectional area. That will give you your actual volumetric flow that's going through. Now, in many regions and many areas, customers will have to report a value of standard volumetric flow, which will require base conditions for those standard conditions and the current or the actual pressure and temperature inside of the pipe. These base temperatures and base pressures that you see here are simply one of many standard conditions that are defined by local regulations. Within the Panametrics electronics, we can accept conventional units such as absolute or gauge pressure. In terms of temperature, it's going to be either degrees Fahrenheit or Celsius. But we can take gauge pressures and convert them to absolute as needed for our calculations. The last calculation we will discuss is the mass flow measurement. As we all know, flare gas densities and compositions are constantly changing in a flare line. It all depends on which process units or purge lines are opened or closed and introducing flow into the flare gas header. The GF868 and the XGF868 flow meters both utilize a patented set of algorithms to determine the average molecular weight of the gas. The parameters necessary for this calculation are sound speed, pressure, temperature, and nitrogen content. With these values, the flare gas flow meter is able to provide a very reliable average molecular weight reading. The algorithms assume a 100% hydrocarbon gas less the amount of nitrogen that's being used as the nitrogen input. If a live value is not available for any of these inputs, a fixed value can be programmed into the flow meter. However, it should be noted that there will be inherent deficiencies of these calculations if accurate live inputs are not being utilized. With knowing the molecular weight of the gas, calculating mass flow is rather easy, as you can see from the equation on your right. Now that we have had some time to discuss the terms and theory surrounding ultrasonic flow measurement, let us take a look at the equipment that is likely in use at your facility today. The enclosures of your flare gas flow meter can come in various versions of these two main enclosures. First, we have the general full-size box-style enclosure known as the GF868. This has a full keypad with soft touch buttons, which makes interfacing a breeze. From analog inputs and outputs to alarm relays, pulse or frequency totalizer cards, and even Modbus, Heart, and Foundation Field Bus digital cards, our GF868 can be loaded with up to 6 additional option cards to expand your data capabilities. This standard enclosure can also be mounted inside of an explosion-proof or a flame-proof enclosure as required by your site's requirements. The XGF868i has a smaller footprint with higher area classification ratings as an explosion-proof or flame-proof enclosure. There's a magnetic interface on the front so you can communicate and have local field display of parameters. Because of the reduced footprint, the amount of option card slots are more limited. Both electronics allow for either single or dual channel flow measurement. They come standard with volumetric flow, molecular weight, and mass flow calculations as we discussed earlier. In addition, both flow meters have a serial communication port standard to allow for laptop communications with our PanaView software. Our ultrasonic gas transducers come in a few variations based on the application. These are a few of the most common transducers we utilize. Additionally, on all flare applications, we recommend using insertion mechanism assemblies, or IMAs, for the transducers. These are the black bell-shaped objects you can see on the backside of each isolation valve. These are recommended for lower pressure applications that are under 80 psi or 5.5 bar. These have a PTFE packing gland, which allows for the transducers to be retracted and the isolation valves shut without opening the line to atmosphere. First, we have the T5 transducer. It comes in either the straight head or 90-degree variation, which is also known as the bias 90. I'll show how these installations look on the next slide. The T5 transducers remain the workhorse of many applications worldwide. With increased accuracy regulations in different regions, Panametrics developed a stronger transducer, the T17, as seen below. The stronger signal allows for us to have longer measurement paths, which, in turn, can offer higher accuracies in flow measurement, particularly at low flow conditions. The stronger signal also allows the T17 to operate at higher velocities without having the signal wash out due to attenuation. Because we offer a wide variety of transducers and installation orientations, we can make many applications work very well. On the left, you can see a compact pipe rack that is utilizing a set of straight head T5 transducers. As a note, the T17 applications would look very similar to this. The right image shows a setup of T5 bias 90 transducers located at the top of the pipe. The transducers enter in from the same side of the pipe and look at each other with their right angle transducer heads. The face of the transducers are aligned with a scribe mark on the IMA flanges to assist with checking alignment during removal and reinstallation. Each of these installations go through our team of application engineers to design the best installation locations, alignments, and configurations for your facility. These applications can use a custom-built spool piece from our factory, or can also be used in conjunction with hot or cold taps on the existing lines at your facility. Here we can see a few different two-path flow meter configurations. There are many benefits for having two measurement paths. For one, two measurement paths can provide up to a 35% improvement in accuracy. More signal that is interrogating the process contributes to the overall repeatability and therefore accuracy of the flow measurement. Next, adding a second path can assist in cross-flow cancellation due to diurnal effects. As stagnant gas inside the pipe heats up and cools down due to external conditions, such as sunlight or just ambient temperature, the gas can appear to roll or swirl around inside the pipe. Because ultrasonic flows can be measured reliably down to 0.1 feet per second or 0.03 meters per second, this rolling may be registered as a slight positive or negative flow. When two channels are being utilized, one will read slightly positive, while the second channel will read slightly negative. The average of these two channels will then show that there is no true flow going through the pipe. A final advantage of multipath configurations is the ability to have a redundant system, allowing for measurement even if one channel is damaged or not reading properly. The first three of these images are various configurations of straight head or 180-degree applications, whether that is a T5 or a T17 transducer. The image on the bottom right shows two T5 bias 90 applications on opposite sides of the pipe. With that being said, I would like to conclude our discussion today on ultrasonic theory and Panametrics flare gas flow meter equipment. Thank you very much for your time and for joining us today. Should you have any further questions regarding training, products, or more, please let us know how we may be able to help at your site. Please stay safe, and I look forward to speaking with you again soon. Thank you.